Imagine tuning a radio and discovering stations playing at pitches so low or so high that no antenna or human ear could ever pick them up. That's the essence of hidden frequencies, forms of energy slipping through the gaps in our instruments forever beyond our grasp. What makes a frequency invisible? Every detector, from your smartphone's antenna to a giant gravitational wave observatory, has a sweet spot, a band of frequencies it can sense. Below or above that band, waves pass by silently. Think of trying to hear a dog whistle. The pitch is too high for our ears, but perfectly clear to Fido. Now magnify that difference by millions or billions of times, and you begin to glimpse why some cosmic signals elude us entirely. Which frequencies hide from us today? Ultra-low radio waves, waves longer than a few kilometers, can't reach the ground because Earth's ionosphere reflects them back into space. We'd need antennas the size of continents to catch those whispers. Super high gamma bursts, photons above a certain energy collide with cosmic background light and transform into particle pairs long before they reach our telescopes. Those extreme GRAs simply never make it here. Dark sector vibrations. If dark matter interacts via hidden force, its dark photons wouldn't nudge our ordinary detectors at all. Any oscillations in that shadow realm remain locked away. Only clues in gravitational behavior hint at their existence. Could we ever detect these phantom energies? Perhaps indirectly. Question: how do we know cosmic rays exist at the highest energies even though we can't manipulate them? Answer: we watch for their footprints. Particle showers in Earth's atmosphere, tiny flashes of light marking their arrival. Similarly, hidden frequencies might leave secondary signatures. Subtle shifts in a star's brightness, tiny twists in a gravitational wave signal, or unexplained heating in ultra-cold detectors. Why does this matter? Because if whole bands of the universe's song are muted to us, our picture of reality is incomplete. We may be missing entire chapters of cosmic history, energetic events, unknown particles, even new forces, simply because we haven't built the right ears. By dreaming up clever indirect methods or by sending detectors into space or to the far side of the moon, we might coax these hidden vibrations into view. Until then, vast stretches of the universe's symphony remain silent, inviting us to invent better instruments and deeper questions. Human senses are restricted to narrow frequency bands, visible light, audible sound, and certain tactile vibrations. Scientific instruments extend this range, but they too rely on physical principles that impose detection limits. Many frequencies lie far outside what can be converted into measurable signals using current technologies. These include forms of radiation or energy that pass through space without interacting with matter in detectable ways. Infrared cameras let us see heat, but we remain blind to neutrino waves that flow constantly through our bodies. It's like trying to hear a dog whistle. Just because it's silent to us doesn't mean it isn't deafening to someone else. Some frequencies are so stretched, due to cosmic expansion, that their wavelengths now exceed the size of the observable universe. These ultra-low frequency waves have periods lasting millions of years, far beyond any detector's temporal resolution. Because light from such sources will never reach us, any energy encoded in these frequencies remains fundamentally unobservable. These frozen signals are lost not because they don't exist, but because we are physically cut off from them. Certain gravitational waves from the early universe have wavelengths larger than the observable cosmos and cannot be measured. It's like trying to read a letter that was mailed from a planet moving away faster than the speed of light. You'll never receive it. Dark matter does not emit, absorb, or reflect electromagnetic radiation, making it invisible across all known frequencies. If dark matter carries its own exotic frequencies, they might never couple with detectors made of ordinary matter. This means entire spectra of dark frequencies could exist, passing through us unnoticed, never leaving a trace. The universe might be vibrating with forms of energy we're not built to perceive. Billions of dark matter particles pass through Earth each second without being detected by any current instrument. It's like a silent concert for an alien audience, playing music on instruments we can't hear or touch. Even when we build sensitive detectors, quantum fluctuations set a hard floor for what we can detect. These background fluctuations, also called quantum noise, blur any signal weaker than their threshold. Frequencies that fall below this noise level, even if real, will always be drowned out. This creates an information horizon where certain signals are permanently buried under uncertainty. A graviton's individual vibration is so weak that quantum uncertainty overwhelms any attempt to isolate it. It's like trying to whisper across a room during a thunderstorm. The signal exists, but it's overwhelmed by unavoidable noise. Physics, as we know it, is based on interactions between known fields: electromagnetic, gravitational, strong, and weak nuclear. But hypothetical fields, such as those tied to higher dimensional branes or hidden symmetries, might operate on frequencies that don't couple with ours. These alien frequencies could oscillate endlessly without ever touching our detectors or matter. We might live in a universe where whole dimensions of frequency are orthogonal. A scalar field associated with dark energy could vary across time, vibrating in a way that no current sensor can translate. It's like someone tapping a drum in another room with walls so thick you never feel the vibration, no matter how loud it gets. Our brains and bodies evolved to tune in only to the frequencies essential for survival: sight, sound, and touch. Evolutionary biology filters out useless or dangerous stimuli, meaning we are literally blind to entire classes of frequency. Even if new sensors detect these bands, our cognitive systems may lack the capacity to interpret them meaningfully. The brain itself is a frequency-censored organ, but it operates on a narrow mental spectrum. You cannot perceive ultraviolet patterns on flowers the way bees do, even with your eyes open. It's like trying to describe a color that doesn't exist in your language. You simply have no way to frame it. Theoretical physics predicts many frequency domains that we will likely never observe. These include oscillations in vacuum energy, compactified extra dimensions, or signals from collapsed timelines. While equations suggest these frequencies exist, they may never produce observable effects. They are real in theory, but practically undetectable due to physical barriers or lack of coupling. String theory predicts vibrational modes of tiny strings far beyond the Planck scale, far too high to measure. It's like knowing there are notes above the range of a piano. You can write them in music, but never play them. Some frequencies are too fast or too slow for detection over human timeframes. Ultra-high frequencies may oscillate millions of times faster than the resolution of our best tools. On the other end, ultra-slow cycles might take thousands of years to complete a single wave, making observation meaningless for any individual human or civilization. These signals exist in a temporal domain outside our experience. Certain black hole spin vibrations could take centuries to complete a single oscillation. It's like trying to notice the movement of continents with your bare eyes. It's happening, but not in a way you can ever see. There may always be frequencies that lie beyond the boundary of what can be perceived. Regardless of how advanced our technology becomes, some energies may exist in forms that do not resemble waves at all, or that do not exist in space-time as we know it. This raises the possibility that human perception, even when amplified by machines, will never be truly complete. The universe may remain partially hidden, not because we fail, but because it's structured that way. A civilization with infinite technological development might still miss certain types of frequencies due to the structure of physical law. It's like reading a book where entire pages are printed in invisible ink. No amount of squinting will bring them into view.